So let me make this little video here. So I just want to talk just briefly here about sequential analysis for you guys. If we have a vector space with a norm, if we have a function from the natural numbers to v, it's called a sequence, right? You have a list of things indexed by n. So let me get straight here to the definition. Oh man, I better set up here if I can get to it. All right, there we go. So suppose we have a sequence, then we say the limit of the sequence is L if and only if for each epsilon greater than 0 there exists an m in the natural numbers, m as in mummy, such that the norm of a sub n minus L is less than epsilon for all n which have n larger than m. You can put equals here, it doesn't really matter. If this limit exists, then we say that the sequence is a convergent sequence, right? So that's not probably too surprising, I hope. I mean, we basically cover that in calculus too, but with real numbers instead of vectors. But now we've got vectors. We can take a sequence of vectors and define them to be convergent if you can find an epsilon. For each epsilon greater than 0, you can find an m such that when you're beyond the m, you're sufficiently close, as close as you like, to the limiting value. All right. Now, this next definition is perhaps new. This is the definition of a Cauchy sequence. A Cauchy sequence, possibly a sequence of vectors here. It's a Cauchy sequence. So here a sub n is an element of the vector space. I don't think I said it, but that's assumed, all right? If and only if for each epsilon greater than 0 there exists an m such that the distance between the mth and the nth elements in the sequence is less than epsilon for all m and n which are larger than your m, all right? So basically what this is saying is that if you go far enough out in the sequence, you can make the difference between terms past that point be as small as you like. All right. So the standard example I always give students to give an example of a sequence which is not Cauchy, all right, which is Cauchy, but it doesn't converge inside the space. I like to use the digits of pi. All right. So if we look at if we look at any truncation of the decimal expansion of pi, that's a rational number, right? Like 3 is rational, 3.1 is 31 over 10, 314 over 100, 3,141 over 1,000. These are all rational numbers, right? And this sequence does converge. It converges to the number pi. If the universe of discourse is the rational numbers, then it converges to a point outside of the rational numbers. So this sequence, the truncated digits of pi, you can prove that this is a Cauchy sequence of rational numbers because the difference between truncated decimals, if you go far enough out, you can make it as small as you like. So this is a sequence which is convergent, and yet which is Cauchy, and yet is not convergent in the context of rational numbers. So when spaces are missing their limit points for some Cauchy sequence, there's in some sense an incompleteness, right? You guys maybe know that rational numbers are incomplete. They're missing the irrational numbers, right? And so that brings us to the definition of a complete space. A complete space is one for which every Cauchy sequence, we can talk about it in the context of a distance function, so a metric space. If every Cauchy sequence in a metric space converges to a point within the space, then we say that the metric space is complete. Similarly, if a normed vector space is complete, we say it is a Banach space. So, and I guess this is a little bit out of place here, but you can define convergence of sequences in a metric space. I haven't even done that in this notes, so this is kind of out of place. My apologies, guys. So let me show you. We're going to assume that the real numbers are complete. Like I mentioned, that is the business of Dr. Joseph in the real analysis class to prove that sort of thing. I don't know if he does, but he might. I mean, I guess I would if I was teaching it, but I'm kind of crazy. So let's see here. Where am I? That's the definition. Okay, so I want to look at example. It's hard for me to see the camera from where I'm sitting. This is an example. Claim, if we know that the reals are complete, that implies that R2 is complete. Okay, so let me lay out the logic here. To prove something is complete, we want to assume we have a Cauchy sequence and then we need to prove that that criteria implies that it's convergent. So here we go. If we have m and n in the natural numbers such that when little m and little n are beyond big N, that implies that the difference between the mth and the nth sequence in the plane is less than epsilon. So we're going to assume that, all right? Then that means, well, by definition, this is the Euclidean norm, so that's that, right? But then, all right. Therefore, where was I? All right. Therefore, as the absolute value of xm minus xn is less than, well, that's equal to that. And you can also see that this is what we were talking about today. The length of the x component is less than the length of, whoa, well, that's a wind. Less than the length of the vector, right? So this is just, but think about this. So we're assuming this is Cauchy, which means we can make this small, but whatever makes this small makes that small because it's smaller than that. So here's the deal. This proves, in fact, that that's a Cauchy sequence, right? Because for each epsilon greater than 0, we can choose n greater than n such that if we're beyond big N, that implies that x sub m minus x sub n is less than epsilon, because we can make this less than epsilon, so that's less than epsilon. All right. So we can do the same for the sequence yn. So what that means is that the x sub n and the y sub n taken alone are themselves Cauchy sequences of real numbers, and by the assumed completeness of the reals, we have that x sub n converges to x and y sub n converges to y. And then I propose that if we look at x sub n, y sub n, that will converge to x comma y. And I give an argument right here, but technically speaking, folks, we could just use the vector limit theorem at this point. Oh, I'm sorry, these are sequences. We don't have that yet. Here's the proof. So let epsilon be greater than 0. Choose n sub x greater than 0 such that, beyond that we have less than epsilon over 2, and n sub y greater than 0 such that if we're beyond that we get y sub n minus y less than epsilon over 2. I can do both of these things because we have already argued that y sub n and x sub n are convergent sequences, which means I can make them as close as I want to the points to which they converge, namely x and y. And as such, if I let n be the maximum of n and y, maximum of, sorry, I'm trying to see where I'm poking at. Ah, goodness gracious. Sorry. Better. Oh, set up here. Where was I? So if I let n be the maximum of the n sub x and n sub y, then for n greater than that, I have the length of this is equal to, of course, this, which is by the triangle inequality less than or equal to that. But I have set up my big N such that I get both this and that is less than epsilon over 2. Add them together, you get epsilon. Therefore, that proves that the sequence x sub n, y sub n converges to xy. Therefore, we have taken an arbitrary Cauchy sequence in the plane, and we have shown that it converges. So that's what you have to do to show a space is convergent. You take an arbitrary Cauchy sequence and prove that implies it's convergent. So if you look at the mechanics of this proof, you can easily modify it for like a matrix to show the set of matrices is complete, because like you'll have like the difference of the mth and the nth matrix here in the sequence of matrices, and it's going to be the case that that's greater than or equal to the absolute value of the mth and the nth difference of a particular component of the matrix. So like if you think once you process what I'm saying here, you can adapt this proof to the matrix thing in the homework pretty directly. Now, so my final thing for us in this little video here is the matrix exponential. So if I look at this e to the a defined to be I plus a squared plus 1 over 3 factorial and so forth, this is the matrix exponential. And to prove that I'm going to prove that converges using the completeness of the set of the matrices with respect to the Frobenius norm, which is the norm I defined last class, by the way, not last class, first class. Anyway, so convergence of a series of matrices is measured by the convergence of the sequence of partial sums. just like in Calc 2. To judge the convergence of a series, we must show the limit of sequence of partial sums exists. So the nth partial sum here is this. And if we have m greater than n, if we take the difference of the mth and the nth partial sum, what happens here is we get just the sum k equals 1 to m minus 1 of that, which is this. All right. So, fine. Notice that this is, I think I asked you to prove that in the homework as well. Sorry, but that might actually be a little bit tough for some of you guys. I will help you if you get stuck. But this inductively extends to the norm of the kth power of the matrix is less than or equal to the kth power of the norm of the matrix. That's something that we can prove. And we're going to need to know this for like next homework too, so just something you want to know about. Anyway, so if I take the norm of the difference between the mth and the nth partial sum, I can use this triangle inequality and this property to get that this is bounded above by this. But that's exactly the difference between, notice that this is a big S, but this is a little s, between little sm and little sn, where little sn is the nth partial sum of this series over here. Now you might recognize that. That's the, you might recognize this here. That is the power series for the exponential. Let me write down something here. That's the power series for the, this power series for the exponential of like norm of A. It's the power series for that. I mean, it's the series, that the power series, I don't know what you want to call it. The series for the exponential. Now we know that converges. Therefore, this is a Cauchy sequence because it's a convergent. It's a convergent. This is the nth. Excuse me. This is the nth partial sum of a convergent series because we know that the exponential exists. All right. So, therefore, since it's convergent, it's Cauchy, and I haven't proved that. That's also true, by the way. Convergent implies Cauchy. You'll prove that in real analysis. So as m and n goes to infinity, we find that the difference between the mth and the nth partial sum must go to 0. And so by the squeeze theorem for sequences, we deduce that since this goes to 0, it must be that that goes to 0. But that going to 0 proves that the partial sum for the exponential of the matrix is in fact the nth partial sum of the matrix exponential is a Cauchy sequence of matrices. Therefore, by the completeness of the matrix space, we then get that the series up here converges using the completeness of the set of matrices. Now, so there you go. Now, in your homework, instead of giving you the exponential, I gave you the sign of a matrix, basically. If you look at the thing I did in the homework, I gave you the power series for sign with a matrix in the variable. And you can mimic this argument to prove that that series converges essentially for the same reason. In fact, if you feed a matrix into the power series for any kind of your favorite, everywhere converging function, everywhere smooth function from like calculus 2, you will get a convergent series of matrices by essentially the same argument. But anyway, that's it. So have a good weekend, guys. Sorry I didn't get to this in class, but I do want to hit differentiation next week, start at the start, and I'm hoping that material is a little bit less intimidating as opposed to this stuff. Anyway, thanks, guys.